So does anyone know anything about C14, and specifically why is it 0? Why does it have a 0 in there? It goes negative and positive, that capital delta C14. 0 is 1950, very close, 1950, yeah. Yeah, and so why is it picked as a reference point for the delta C14, or for C14 in the atmosphere was 1950? Because the nuclear bomb tests, right? The atmospheric bomb tests, exactly, right? And so we have a reference point of 1950 because it was before we started polluting the atmosphere with all this radiocarbon in the Cold War, right? All those above ground nuclear bomb tests. There was a tiny bit that was released in the Hiroshima and Nagasaki bombs, but that was small compared to the weapons testing that was done in the 1960s. Okay, and so we enriched the atmosphere in C14 during the nuclear weapons testing. The negative values mean that, what does the negative values mean? It's older than 1950. Okay, there's less C14 in those samples than 1950. Right, and so we can go into more details on how the C14 ages are calculated. Actually, they use tree rings to calibrate the radiocarbon ages. Okay, I just want you guys to remember that. The tree rings are a more accurate recorder of years than the radiocarbon. Okay, so just you're not hearing me wrong. We need help. Isotopes need help from natural systems. Yeah, Kelsey?
Is the big delta just like what you use with C14?
It just means that the difference, like the difference, right? So we've probably seen that. It's basically saying that this is the C14 in the sample minus the C14 in the atmosphere in 1950. And so instead of little delta, they just use big delta.
It's the difference between like what you measure and the ratio or the delta C14 in 1950.
Yeah.
Like that's their standard sort of.
Yeah, and which is set to 0. Right, so it's just a different scale. And they use capital delta instead of little delta. And I don't really know exactly why. Right, so it's, okay, and so good. So now we know a little bit about C14 and how useful C14. I'm pretty sure, but what we need to, right, and so if you think about it, right, so here we've got an enrichment relative to the 1950, and here we've got a depletion relative. And so this is actually another thing to, I guess, point out is that this is a really, really lot of radiocarbon, right? That's a lot of radiocarbon. So there was this massive, and this is another whole topic that I didn't really prepare a lot of background on, but it's been very useful to try to understand the dynamics of soil organic matter and different types of carbon pools in ecosystems. Also in the ocean, right? So a lot of that radiocarbon rained down on the ocean, and it's helped us understand the different layers, the mixed layer and the shallow layer, and the different ages of the ocean circulation and so on and so forth. Yeah.
Is this kind of dating useful for anything like a lot younger than 1950?
Okay, it's not actually, it becomes, okay, since the bomb tests, since about 1960, we can get pretty good high resolution, but the thing is now it's the bomb spike, what they call it, is running out. And so those differences are becoming smaller.
So are you expecting to take on time that it's going to be like a U-shape that's going up?
No, the bomb spike is decaying, right? Since it's radioactive, it's decaying. Okay, and so I can tell this is, so some other years, I know that Sue Trumbore used to come and lecture in this class, specifically focused on C14, and it's a big topic, and but I don't want to steal time from the methane section of my lecture, which is going to happen if we keep going on this. But so I'm just going to suggest that you guys try to, if you're interested in these things, understand that this is another whole tool. It's another isotope, right? We're going to learn about O17 and clumped isotopes. C14 is another isotope that it's radioactive, but it is also becoming cheaper to get analyses done. It can be quite expensive, but it's becoming cheaper, and it can give you insight into carbon cycling processes in a lot of different ecosystems. Okay, good. And so now, since we can see that this high delta C14 stuff is young, right? So this is the young, fresh stuff, and this is the older pre-bomb carbon. And we can see that, again, the delta C13 value of those organic matter pools are increasing with age. Okay, good. So and so Jim Elringer actually in 2000 wrote this nice little review paper with a couple of postdocs and sort of summarized a number of these different hypotheses and to try to help explain why the delta C13 value of organic matter increases with age, with depth, and with the insides of the aggregates. And so one explanation is because the delta C13 content of the atmosphere has been changing over time. Okay, so we're just talking about the delta C14. What about C13 and the CO2 of the atmosphere? It's decreasing, right. It's decreasing because of fossil fuel burning, exactly, right. And so what does that mean about the older soil organic matter? It's relatively enriched, right? So some of that older soil organic matter could be enriched partly because of because it was formed in equilibrium with, from photosynthesis, derived from a more enriched atmosphere, because now the atmosphere is becoming more depleted, right? But that actually can only explain maybe 1 or 1.5 per mil. In that soil in Oregon, we saw that it was about 4 per mil different, right? There's a 3 or 4 per mil increase that's often seen. Okay, so that's not going to be the whole explanation. It could be that microbes, when they're doing the decomposition work, they actually favor, keep the C13 in the soil organic matter, and more of the C12 is lost. That could be part of it. Actually, it turns out that the microbes themselves might be partly contributing to this enrichment because bacterial lipids are more enriched in C13 than fungal lipids, and bacteria become more abundant with depth in the profile. I don't know if that's going to explain the age thing, but it may be the depth observation. And another thing that's actually, I tend to favor, there's microbes carboxylate CO2. There's carbonic anhydrase that basically dissolves CO2 and incorporates it into solution. And then that can basically incorporate CO2 from the environment, and it makes microbial biomass heavier than the soil organic matter. And so this is another, I think, an important thing to consider when we realize that a lot of that old soil organic matter is just microbes, right? It's just microbes.
So I think it was in Jim's lecture where he talked about this a little bit. He basically was talking about how you can get kinetic fractionation, but that it's not really seen when you try and measure it.
With the soil CO2.
Yeah.
Right, and so I think that Naomi or Katie might be talking about CO2 diffusion kinetics, maybe not. Well, and we'll talk about this more in my group, but right, so the thing is that there's definitely going to be kinetic fractionation due to diffusion. It turns out that it's about 4.4 per mil, like the theoretical amount of diffusion fractionation is 4.4 per mil. And so when you measure the CO2 in soil right next to where it's being produced, that kinetic diffusion fractionation does exist, and we will hopefully observe it. But the thing is that when you're measuring it off the surface of the soil, it's going to be at steady state. And so what's produced, leaving the soil is going to be the same as what's produced in the soil. And so it is actually at steady state with the source material.
If anyone wants to talk, we see that fractionation, that 4 per preserved actually in those carbonates, those aerosols that Elise was mentioning. We actually see that 4.4 per mil or some variants of actually preserved in geologic record because we're not actually getting what's coming out of this soil. We're actually locking in soil CO2. So there's too much to talk about for us to all cover, not all lectures, but if you guys are interested in that component from the geologic record, then I go talk to you.
Right, good. And so O18 can also become fractionated in soil carbonates, and that's a bigger fractionation, right? Because it's double the mass. Perfect. Great. Yeah, you guys are connecting a lot of dots here. It's really great. Okay, good. So, and so there's probably a number of processes that are leading to this observation in natural abundance, C13 in organic matter that increases, the C13 increases with age, with depth, and inside of aggregates.